What we are going to prove in this pencast is the following statement. If a real valued function has bounded slope on an interval of real numbers, then the function is uniformly continuous on that interval. So let's state that more formally. This statement of the proposition. So the idea with this pencast is we'll look very carefully at how to prove things, and this is just one example of how to prove this particular statement. So here's the statement as I'd like it to be. Let capital J represent any interval of real numbers. I'll define this more carefully later for those needing that. And then we're going to suppose that we have a function f that sends elements of the interval j into the set of real numbers. We just say that f is a real valued function. Defined on the interval j. But we want a few extra conditions on this function, namely that f is a function so that f is differentiable on j, so that f has a derivative. And beyond that, we also are assuming that the derivative f prime is bounded on j, which just means the value of the derivative on that interval only gets so big and only gets so small. And we'll write down what that means specifically or in the near future here in this pencast. Anyway, the conclusion is when you have all this going for you from here to here, then this function f is uniformly continuous on j. So now we have a formal statement of the proposition. Before proving this proposition, we'll do a couple things. First of all, why would this statement be useful? Well, it gives us an easier way to prove some functions are uniformly continuous, easier than using the definition to prove they're uniformly continuous. We can just check whether the derivative of the function is bounded. So for example, let's do an example application of this theorem. Example application. Okay, so let's consider the function f that goes from the real numbers into the set of real numbers be given by the function f that's given by the formula f of x equals the inverse tangent of x, or the arctangent of x. Then we know from our Cal 1 that the derivative of f is 1 over 1 plus x squared, or all real numbers x. So now we want to check that the derivative is bounded, and the way the definition of bounded goes, which we will discuss shortly here, we would just take the absolute value of the derivative and hopefully be able to prove that it's less than or equal to something. Well, this particular derivative, it's already positive, so we know that's just going to be equal to 1 over 1 plus x squared. But in particular, 1 over 1 plus x squared is going to be always greater than 0, but strictly or less than or equal to 1. Why is that? Well, because here on the side I'll explain that. X squared is definitely going to be greater than or equal to 0 for any real number x. So in particular, 1 plus x squared is going to be greater than or equal to 1. And taking reciprocals of both sides, how does 1 over 1 plus x squared compare to the reciprocal of 1? Let's see, the reciprocal of 1 is just 1. And when you take reciprocals, that reverses the order of the comparison for positive numbers anyway. And so what do we get? Now 1 over 1 plus x squared is less than or equal to 1. On the other hand, we know x squared is greater than or equal to 0, so obviously the denominator being greater or equal to is greater or equal to 0, and a positive number divided by a positive number is positive, so the fraction is going to be positive. It can't equal 0 since the numerator is not 0. Now, after all that, in the end, basically what we've shown is the absolute value of the derivative is less than or equal to 1 for all x in the interval that this function is defined on. This interval is the entire interval of real numbers. And therefore, by the theorem, or by the proposition, we're calling it here, therefore, by the proposition, it will be true that the arctangent function is uniformly continuous on the interval that it's defined on, the interval of real numbers. So the arctangent function is uniformly continuous on the set of real numbers. So, before we actually do the proof, let's talk about the ingredients for this proof. And by that, I mean we're just going to discuss the terminology and any previous results that we know we can reason with. The ingredients of the proof. So, pardon me if I can put too much detail in on this, but let's see, what do we need to know? It's like, what type of interval are we talking about? J is an interval, so let's make sure. I didn't really specify what type of interval, so it could be an open interval, which is has a form like open interval from A to B. It could be a closed interval from A to B. It could be an open array, by which we mean it'd be like an open interval from A to infinity, or it could be an open interval from minus infinity to some number B, not including B. Or the interval could be a closed array, so it'd be the closed array from A to infinity, or the closed array from minus infinity to number B. In this case, the endpoints are included. Another thing that's useful to remember at some point in the proof is that, I'll just say, recall, this is a fact from Calculus 1, that if f is differentiable, on an interval J, then f is continuous on J. So basically, we're assuming our function, in the statement of proposition, we're assuming f is differentiable. So we get for free from this theorem of Calculus 1 that f will also be continuous on that interval, even though it's not explicitly stated so. Now, what are we trying to prove? We're trying to prove that f is uniformly continuous on this interval J. So what is the definition of that? We say a function from the interval J to the set of real numbers is uniformly continuous on J, provided the following happens. For all positive numbers, epsilon greater than 0, there is, or there exists, a delta greater than 0, such that for all x and y in the interval j, if the distance from x to y is less than delta, then the distance from f of x to f of y is less than epsilon. And we could come back up here and put all that in symbol forms. This is usually abbreviated like this. For all epsilon greater than 0 is abbreviated like this. What's supposed to happen for any epsilon greater than 0? For each one that we pick, there's a delta greater than 0. That gets abbreviated this way. For all x and y and j is abbreviated. For all is the upside down, capital A. X and y are both elements of the set J, so we can use set notation to abbreviate that. And finally, we have an if-then statement that would go like this. If-then statements are written as follows. You write the if part, and then an arrow, and then the conclusion part. I didn't leave myself enough room there. Oops. Well, anyway, so that's the symbolic form. Usually it would even be written in one long line. For all epsilon greater than 0, there exists a delta greater than 0, such that, the words such that aren't written in the logical form here, the formal logic form. For all epsilon greater than 0, there exists delta greater than 0, such that for all x, y, and j, the absolute value of x minus y less than delta will always imply that the absolute value of f of x minus f of y is less than epsilon. And remember, those absolute values of differences are distances, so you can restate that implication in terms of distances. I'll go through the whole thing again. For all epsilon greater than 0, there exists a delta greater than 0, such that for all x and y in the interval j, if the distance from x to y is less than delta, then the distance from f of x to f of y is less than epsilon. Finally, there's one more result from Cal 1 that I want to remind you of before we do the proof. The mean value theorem for derivatives. Alright, so how does this one often get stated? Something like this. If you have a function g from the closed interval from a to b into the set of real numbers, and we know that function is continuous, and we know that g is differentiable on the open interval from a to b, then we can conclude that when we take f evaluated at b minus f evaluated at a and divide it by b minus a, that will equal the derivative of f evaluated at c for some c between a and b. And usually, to make the way kind of to remember this theorem is intuitively, sure, if you have a function that's continuous from a to b, say the graph of the function would look something like this, starting at above x equals a and going to some point above x equals b. That's the graph of f of x. Then we look at this line connecting the endpoints, and the slope of that line is going to be, well, you would take the difference in the y-coordinates at each point. So the y-coordinate of the point with x-coordinate b, the y-coordinate is going to be f evaluated at b. And when x equals a, the y-coordinate at the left-hand endpoint over here is going to be f evaluated at a. So I'm taking the y-coordinate of the second point and subtracting the y-coordinate of the first point over here, and then dividing that by the difference between the x-coordinates. So that's going to be the slope of that line. Now if you look at the graph of the function, which remember is here, I'm trying to trace over it again, you can see at some point along there, if you're imagining all the tangent lines, some point along there, there's a tangent line that is parallel to this dashed line. So if we locate that point of tangency and call the x-coordinate c, then the slope of the tangent line, the slope of that tangent line is going to be g prime evaluated at c. I forgot I was calling my function g, so we have to go back and make all of these f's right here g's. That should be g. Okay. Just agree with the original letter of the function. Anyway, this is the important thing. G of b minus g of a divided by b minus a will be equal to g prime evaluated at c for some c between this b and this a. Okay, now I think we're ready for the proof. So we're assuming that we have all this stuff in the statement of the theorem, all the assumptions there. Let f be a function from the interval j to the set of real numbers. Alright. And such that f is differentiable on j, and f prime is bounded on j. Okay, well, I didn't tell you yet, give you the formal definition of what bounded means, so let's remind ourselves of that. But basically, we can start the proof with that kind of, what's the conclusion that we're aiming for? What are we trying to prove? F is uniformly continuous on j. So f prime is bounded. That tells us, since f prime is bounded, the absolute value of f prime of x is less than or equal to some constant, I'll call it capital K, where K is a positive real number. And that inequality is going to hold for any x in the interval j. So there's a uniform bound to the value of the derivative. It's not going to get bigger than plus k or smaller than minus k. Now, we want to show this function as uniformly continuous. To show something's uniformly continuous, I need to pick an epsilon greater than 0 and show that I can find a delta that doesn't depend on any x or y, just depends on epsilon only, so that all these other conditions about uniform continuity follow. So we're going to let delta equal epsilon divided by this constant capital K. And since K is positive, I can divide by K. So now I'm going to suppose that I have an x and y from the interval in J, and suppose that they're less than, the distance between x and y is less than delta. So the absolute value of x minus y is less than delta. And then I'm going to say that I'm going to look at the absolute value of f of x minus f of y. And let's see, I know that's going to be equal to the absolute value of f of x minus f of y divided by the absolute value of x minus y times the absolute value of x minus y. That's just multiplying by a factor of 1, basically. I am assuming here that x doesn't equal y. If x does equal y, then obviously the difference between f of x and f of y would be 0, so that's going to be, the absolute value would be less than epsilon in that case too. So now, well, if we look at this a little more carefully, then the absolute value in a fraction, we can write that as a single absolute value of the absolute value of f of x minus f of y over x minus y, and then we have times the absolute value of x minus y over here. The first absolute value is supposed to remind us of the mean value theorem. So anyway, this step was property of absolute value. The next step is going to be because of the mean value theorem for derivatives. I'm going to say we can replace this by f prime evaluated at c for some c between x and y. If it doesn't whether x is smaller than y or y is smaller than x, either way, c is going to be between them. But now we know from our assumption up here that the absolute value of the derivative is less than or equal to k. So that's less than or equal to k times the absolute value of x minus y. But on the other hand, we've assumed that the absolute value of x minus y from up here is less than delta, right? So that's going to be, I guess I can put strictly less than here, actually. Less than delta. But how did we choose delta? Delta was equal to epsilon over k. And what's k times epsilon over k, of course? Epsilon. So anyway, that's a long-winded way of saying basically if the absolute value of x minus y is less than this delta that I chose, epsilon over k, then the absolute value of f of x minus f of y is less than epsilon. So what I've shown you from here down to here is the following. No matter what epsilon I pick, for any epsilon greater than 0, I can find there is a delta greater than 0, so that no matter what x and y I pick from j, as long as the distance from x to y is less than delta, then the distance between f of x and f of y is less than epsilon. And in shorthand, we just use the phrase f is uniformly continuous. Okay, so hopefully there's enough detail in there for everybody, and just remember to skip what you don't like on any other pencast proofs like this. Thank you for listening and watching.